So back to the factors in rectangles. So we're finding the relationship between the rectangles we can make with a given set of blocks, a given set of squares, and how that relates to the list of factors, and they're one and the same. Factorization versus prime factorization. Let's play around with a few of these here and then try to answer the last three questions. So we played with 51. We didn't play with 53 together yet. 24 was one of the numbers you had to work with. So a couple of things I can do with 24. If I factor it in pairs, 1 times 24, 2 times 12, 3 times 8, 4 times 6, 5 doesn't work, and then I'm back to 6. So this gives me all of the factors of 24. If I do a factor tree, that's where I like to start with the smallest prime, 2, if it works, and 2 does go into 24 12 times, and then I keep dividing the 2 out until I'm done with it, and this one goes quite a ways. And the ends of the branches here give me the prime factorization. So based on that, I can say 24 is equal to 2 times 2 times 2 times 3, or I could write it as 2 cubed times 3. Either one of these is a prime factorization. All of these other ones are just other factorizations. So there's lots of possible factorizations. So 3 times 8, for an example, is a factorization for 24. How about, let's see, 2 times 3 times 4? Is that a prime factorization or just a factorization?
A factorization.
It's just a factorization because 4 is not prime, right? And somehow my chat vanished again. Where is it? Not here, not there, not there, not there. Huh. Okay, maybe it will reappear when someone chats. Sorry about that. Don't know where it went. All right, so again, this is a factorization. What about, let's see, 53? What did y'all find out about 53?
That it's a prime number?
Is it prime? Okay, it looks prime to me. Let's see, 1 times 53, and then 2 doesn't work. 5 and 3 is 8, so 3 doesn't work. Since 2 didn't work, all even numbers are out. So next I would check 5, nope. 7, nope, because 7 goes into 49, and that's too close. 11 would be next. 11 goes into 55, so that won't work. The question is, how far do I have to look? And the answer to that, I'm going to stop right there for a minute, is related to the stopping point here. Notice how close 4 and 6 are together. Now, numbers aren't always that close, but let's see, where's 36? That was the nice one for an example. 36 stopped when the exact same number happened. And an important relationship here is that 36 is equal to 6 squared, which I can alternatively write as 6 is the square root of 36. And the square root is nice because that's the exact same number. So if I know the square root of a number, then I know the turning point for factors. And it turns out that works all the time. So as far as when do I stop looking, are 7 and 11 far enough to know that 53 is prime? The answer is, well, what's the square root of 53? Unfortunately, we can't do that easily without a calculator. It's possible, but challenging. So SQRT 53, Google Calculator says it is 7.28. So once I get to 7, it turns out that's far enough. 7 squared is 49. It's reasonably close to 53. Therefore, I'm done looking for factors. So this is around 7. So we are done looking. 53 is prime. So that's kind of a nice trick. The turning point could be a number by itself, which is the definition of a square root. So find the square root, and that tells you how far to look. Otherwise, without that idea, I'd have to keep looking until I got close to 53. But that factor list helps us figure that out. Yeah, so 53 is prime. Okay, now, here is an interesting question. What is the prime factorization of 53? Anybody?
Would there not be one since 1 is not?
Yeah, see, we want to write 1 times 53. At least I do, but 1's not prime. So it's like, oh, I can't do that. So if I write just 53, well, it's not a product, so I don't have a factorization. So it's really just not a good question, it turns out. There's no great answer to it. If you write 1 times 53, that's inaccurate because 1's not prime. If you write 53 on its own, is it really a factorization if you have only one number? That's questionable, but I think this is the better of the two options, to just say, it's 53. It's prime. It doesn't break down. 1 is boring. Okay, so now for the fun questions at the end. And those questions were, what kind of numbers have 2 factors? What do we call those? Those are, I think everyone's got this one somewhere.
Prime numbers.
Yeah, those are the prime numbers. And numbers that we found that had 2 factors so far were 2, 3, 5, 7, and 11. And we skipped a few and then ended up with 53. Oh, I guess we found 17 in between there, didn't we? Then there were more than 2 factors. And what are those called?
Composite.
Composite, yes, those are called composite. And composite numbers we've accumulated so far are, let's see, 4, 6, 8, 9, 10, 12. Let's see, we got 24 was one of the numbers we played with, and 51. There's probably a couple others on that sheet somewhere. And the last question I thought was kind of fun. What kind of numbers have 3 factors? And question number 6 had us list those numbers, and they should have been 1, 4, and 9. And 1, 4, and 9 have something special in common related to the work we've been doing. They have 3 factors. And or even, actually, that's not the right question, not 3 factors. It's supposed to be odd number of factors. I misstated that completely. Odd number of factors. Not 3 factors. So let's look back at some of those, right? 1 has, the only factor it has is 1. 4 for factors had 1, 2, and 4. 9 for factors had 1, 3, and 9. And other numbers, like when we looked at the factors of 12, 1, 2, 3, 4, 6, and 12, they made these pairs for the rectangles. So what's different over here than with these composites and primes? And I heard someone say it in another group. What might be the next number in this list? No one sure about that here? All right, let's play a little bit. So let's see, numbers we didn't get to yet. 13, 1 times 13, that's prime. 14, let's see, that's a little bit more work. 1 times 14, 2 times 7. And I think that's about it, because 2 and 7 are prime. 15, 1 times 15, 3 times 5, 3 and 5 are prime, so I guess I'm done. And I guess equals isn't the appropriate symbol there. 1, 3, 5, and 15. 16, let's see, 1 times 16, 2 times 8, 4 times 4, that's a repeat. So its factors are 1, 2, 4, 8, and 16. Oh, it has 5 factors. An odd number of factors. It's not and, but an. What's different about 16 than these other numbers besides it's an odd number of factors there?
We got a couple chats. I don't know if you can see them.
I can't see the chat and it's not even alerting me.
So Amanda has square numbers and Mason agrees with Amanda.
Thank you. Where is my chat? Ah, okay. I find it on my other screen behind another Zoom box. Thank you. Sorry I couldn't hear that or see it. Yeah, that's it. If I have a square, instead of having 2 distinct factors, those are the same factors. So it only gets listed once, forcing an odd number of factors to happen. And so that is the key there. If there are an odd number of factors, the next number would be 16. These are perfect squares or square numbers. Oops, perfect squares. Yeah, that's the correct answer there. Good. Well, I think the best answer. There are probably some other answers, but that's all I got off the top of my head. Cool. So I think we have tied up this activity and we are ready to move on. So I mentioned before that the activities are set up a little bit different. The submission is through the submit button. And if I set it up right, you should have the option of file upload or text entry for your stuff. And you can submit more than once. So if you submit some stuff, so there's my stuff and I submit it. But then I decide I want to submit some more stuff, I can just hit resubmit and then you can submit some more stuff. And I'll see you have multiple submissions. I'll look at the newest one, and if I need to, I'll look back from there. So if you submitted this earlier and you decide you want to submit again, go for it. Please do. All right, other questions on this activity?